Here we are, folks. This is the third lecture of the first lecture, so part C of lecture 1. So what we're going to do in this lecture is kind of give an overview of the course and then introduce the first topic, which is memory. Okay, so there are essentially two types of memory out there. I made these definitions up, so don't use them in an interview or anything like that. Essentially, I call it incidental memory and structured memory. So incidental memory is just kind of small memory, such as flip-flop here and there, or a register. But what we're kind of moving towards today is structured memory. Structured memory. So structured memory, it's relatively large compared to what you'll see in registers and flip-flops, and typically it's RAM and ROM. Okay, so structured memory, very simple concept. It's analogous to using arrays in a higher level programming language. And essentially, it's just a set of registers. It's an array of registers where each register has its own particular address. So the address is kind of analogous. Address is a hardware term. It's analogous to using the word index in a higher level programming language. So this is the most generic memory you can imagine. In all honesty, it's out there in the real world. There's a ton of different types of memory, way more than you could ever imagine getting into. We're just going to kind of simplify this as best we can in this course. And the idea here is you'll know enough such that if you ever need to interface with some special memory, you'll know how to do it pretty easily. So anyway, this is a generic memory device here, and I've divided the input and output signals of this thing into three categories. Essentially, it's data, and here's the data lines. Data is going to come in and out of this thing. I'm going to essentially store data. Memory can store data, so I need to get data in and I need to pull it out. I only put one line here. This is the bidirectional line. I need to be able to specify which data I need to put in, or where I need to put it, or where I need to grab it from, so it has an address. And essentially that's analogous to an index in programming language. Also, it's actually hardware, so I'm going to have some control signals here to help me access the data. There's two types of operations you can do with memory, which is read and write. Reading means I am copying something from memory to the outside world. Essentially, that doesn't change memory. It just gives me ability to grab that memory, bring it to the outside world, copy it somewhere else, or do whatever I need to it. Also, I can write memory, which means take something from the outside world and put it into memory, load it into memory, write it into memory. That's an operation that necessarily changes the data in that memory. So at a particular address location, if I'm writing data to that address location, that data is going to change. So this is more specific information here. Generally speaking, what we're interested in is memory capacity, and pretty much how that memory is how I can get at that memory. Okay, so essentially capacity is just a notion of how many bits, how much data, however you want to say it, that memory can store. So each memory is going to be different, but they do have some commonality here. So this is kind of some of the lingo that typically we use with memory. So the first thing is words. So we're passing data back and forth to this thing. Generally speaking, we don't pass it a bit at a time. So we use the notion of a word to signify the smallest chunk of memory we can get in and out of this thing at one time. So just these memories are typically not bit addressable. Typically they're buses. They have widths greater than 1. And so that's what we're indicating here. So the word length is the width of the input and output data that this memory is storing. So yeah, that's S right here. Okay, so this thing has address lines. Address lines are form the address that gives me access to a specific piece of data. It has a special relationship. The number of words a memory can store is related to the number of address lines, and it's always a binary exponential relationship. So for example, if there's 10 address lines, I can store 2 to the 10th pieces of data. And the notion here is with a 10-bit number, I have 2 to the 10th unique combinations of bits that form that number. That's going to form my address. So once again, the address lines are always determine how many words a particular memory can store. The total capacity in bits of any memory is 2 to the number of address lines times the word length, and S here is the word length. Okay. So this is just a chunky example here. I didn't get the numbers right. That somehow passed me by. So lots of times we're interested in the capacity of memories, and oftentimes it's pretty funny because the capacity is given in bits, even though the memory is not bit addressable. It makes the memory sound bigger. You see that all the time. So these are 3 different memory specifications here. I'm interested in the bit and byte capacities, and so I'm going to try to do this in not using my tablet. I'm using the mouse, which never works. So essentially the bit capacities are what's written here. Each of these is a bit capacity. As far as the byte capacities go, all I have to do is divide each of these by 8. Okay. And once I divide each of these by 8, these equivalent numbers here become the byte capacities. Okay, so I guess the only other thing to say in this one is a byte is 8 bits. Everyone knows that. That's written in stone. The issue here is when you use the notion of a word is not defined. Whoever uses the notion of word has to tell you what they're meaning by a word. Oops. Okay. So there's bajillion types of memory out there, but they fall into 2 categories, and it falls into categories of ROM and RAM. So it's read-only memory and random access memory. Okay, so these names are not true to form here. Essentially, they're both random access. So I always ask this when I'm teaching in a real class: is what does random mean? And pretty much no one ever knows. And the notion of random means, I think it's on the next slide here, is that I can get at any piece of memory in the same amount of time. So essentially, semiconductor memory is going to be random access, but something like a tape drive or a hard drive that's spinning is not going to be random access. It's going to take a different amount of time to get at data, depending, like, for example, where in the tape I am, or where the read-write head on the disk is at any one given time. So luckily all that's going away with solid-state drives. But we're still left with RAM and ROM. This is something you got to take away. All the memory out there essentially falls into these categories, and so you got to know this stuff. So RAM, it's read and write. Certainly they're both random access, but RAM, read and write, and it's volatile. So essentially RAM, you turn off the power, you lose the data. Okay, so ROM is read-only. Typically speaking, you can't write it, but you turn off the power, turn the power back on, and your data is still there. So there's a lot of gray areas here, like your thumb drive. It's considered ROM because, you can write it, of course, but essentially you pull it out, you take the power away from it, and your data is still there when it comes back. So this is the final word here. This is what you want to take away from RAM and ROM. These are very, useful definitions. So we are going to be working with RAM in this class, and this is RAM, random access memory. This is my foundation module for RAM. So we can go through it. It has data coming in, data coming out, And what we have here is a set of control lines. So here are your address lines. Here is a write enable. Typically these don't have read controls on them, and lots of times most of the times they're synchronous. So we have a clock in here. So these are the control signals, data coming in, data coming out. I have no status signal on this one. Yeah, so if someone hands you some type of HDL model, you need to look at it and see what the characteristics are. We're going to look at one here in a sec here. So this is a single port RAM. I call it a single port because we're going to work with dual port RAMs or multi-port RAMs. But this is just a simple device here. This is the code I pulled off one of the modules that's sitting online. Not a big deal, you don't have to write this, but you should get a feel for what's going on in this thing. So the issue here is this is very analogous to an array in a higher level language. Essentially, I got a bunch of things that I'm storing, and those things have a width. Okay, so you can see it here. This line right here is the width of my data. This address here, 2 to this number here, is the number of things of this width I can store. So n here, 2 to the n is the number of things I can store because it's associated with the address. The width of those things that I'm storing is m. So this is going to be essentially a 2 to the n by m drive. Let's see, 2 to the Nancy by Mary drive. Oh, so this is a typical Verilog here. I'm parameterizing this. These are the default parameters. If you don't change them, you get to use these. Essentially, I'm going to tell you right now, anything you do in this class, don't change the parameters. What you want to do is change them when you instantiate the module. You never want to go change these things. So inside this module here, essentially what I do is declare a giant array. Essentially, the array it's this many things, and each of those things are that wide. So this is the width of the data. This is how many things I have. Below here, I have 2 things that a memory can do. It can read and write. So let's look at the read. It's easier. All it's doing is going into that array, essentially, as I declared it, using the address as an index into that array, and putting the data on the data out input. Here's the data out input. So that's essentially, by the way it's written, this has nothing to do with the clock. It is by nature asynchronous. But check this out. This is the write. The write, by the way it's written, is going to be synchronous. You can see the pause edge clock there, which makes it a sequential circuit. And the writing is dependent upon this other control signal, which is WE, which is well known as write enable. So if the write enable is turned on and I have a positive clock edge, it takes that input data and writes that input data into some address in memory. Again, that address is given by the address lines. So this is my generic dual port RAM or single port RAM module. We'll be using that in the first experiment and give you a feel for working with memory. So yeah, and this is the top level diagram, the RISC-V architecture. Here's a memory module. Here's another memory module. So what we're kind of interested in is these 2 memory modules. These are actually given to you, but they're very similar to the model we just looked at.